Welcome everyone. Today we're going to be looking at the third definition of a mole. We already know that a mole can equal a mass. We know that a mole is equivalent to a very specific quantity. And now a mole is equal to a volume. In order to understand the definition of a mole as a volume, we first need to discuss Avogadro's law. Avogadro's law is an experimental gas law that relates volume with the number of gas particles. And the symbol that we use to represent number of gas particles happens to be a lowercase n. After some experiments, Avogadro's law really states that equal volumes of all gases at the same temperature and the same pressure have the same number of particles. Now, how we got to this point and how we get to our definition of a mole, we need to look first at his experiment. So his experiment included filling containers, and in our case it's going to be balloons, of different gases. Each of these containers are specifically at the same temperature and the same pressure. So we're going to say that they're at STP. He decided to fill each of these balloons at the same volume. So you'll notice that in each of the balloons, whether it's A, B, C, or D, it's going to have a volume of 22.4 liters. Now, he noted something very important as he was observing these balloons or containers that were filled to a volume of 22.4 liters. He noticed that no matter what gas he put in there, something remained constant. He kept seeing the same thing over and over. So let's take a look at balloon A. Balloon A is filled with helium, which is a monoatomic gas. And if we could see inside the balloon and look at the particles, we could see that they exist there. And what Avogadro noticed or determined was that the number of particles ended up being 6.02 times 10 to the 23. And in this case, the units are going to be atoms. When he filled a different balloon with a different gas, so now H2, which is a diatomic gas, he still noted that if he could see inside, that the number of particles was still 6.02 times 10 to the 23. And in this case, it's molecules. Even when he put in compounds and not elements, so something like CO2, which is actually a covalent gas, if we could see inside and look at the particles, it would look something like this. But he also observed that it still had 6.02 times 10 to the 23 molecules inside. And then even neon, which was a noble gas, which was inert and non-reactive, at a volume of 22.4 liters, he still saw or observed the same thing, that the number of gas particles is still going to be 6.02 times 10 to the 23, and in this case it's going to be the units of atoms. So what's important about this experiment is that regardless of the size or the mass of the gas, we see that the number of gas particles will be exactly the same as long as the volume of the gas is exactly the same. So by using this experiment, we're able to get this idea of a mole equivalent to a volume. And for our cases, 1 mole is equal to 22.4 liters. That's what we decided, or he had decided, after his experiments with all these different gases. 1 mole is specifically going to be a volume of 22.4 liters. Now, Because this is now going to be our definition, we are also going to encounter more conversions. So just like we did before, we could see a conversion from a mole to a volume. And I'm going to show you the two different methods, and you're going to choose whichever one works for you. So our sample problem says how many liters of gas are in 0.32 moles of carbon dioxide at STP. Now, it's important to know that carbon dioxide is a gas. They do mention it in the question, and you should always see something about STP. Because we want the temperature and the pressure to be exactly the same, we're going to hold it at this specific standard temperature and standard pressure. Now, I'm going to use the method of dimension analysis. So I'm going to take what I'm given. Well, first I'm going to make the dimension analysis T, and then I'm going to take what I'm given and put it here on the left side. Now, on the right-hand side, I'm going to use that conversion factor of 1 mole is equivalent to 22.4 liters. And by setting it up this way, with mole being underneath the T-chart, I see that the units of mole cancels out and leaves me with the unit of liters, which is what I want. I'm going to end up multiplying across and dividing down, and I should end up with an answer of 7.168. Now we need to evaluate for sig figs. The digit that's given in the problem has 2 significant figures. So that means my answer must also be in 2 sig figs. So it always works the same way. We start on the left-hand side and we start counting the first significant number. 1, 2, and then the number after I get to that 2 is my helper number. That number is very large, so my answer ends up being 7.2, because I have to round up, liters. So they are my correct units as well. And you can write a capital L. If you want to just write the word, you can write the word as well. Okay, so now let's look at it in the reverse. Let's look at a given volume and converting it to a specific number of moles. And I'll do a proportion in this way. You'll notice that the question says at STP. That's important. We talk about neon gas. That's also important. So I'm going to set up my proportion using what I know. And I'm going to set up proportions 2 ways, because some of you actually do it differently, and I want you to understand that they're exactly the same math in the end. I could go down, which means I set up my proportion where the equivalents are below each other. So 1 mole equals 22.4 liters. The other part of the proportion would be, I don't know how many moles 84.72 liters are. Or you can write a different proportion in which you have the equivalents going across. So you could easily just write it 1 mole is equal to 22.4 liters, but I don't know how many moles is in 84.72 liters. Regardless of how you set up your proportion, you're still going to have to cross multiply. When you do the math correctly, you cross multiply, you divide, you do what you need to, you end up getting as your answer for x to be 3.782142857. Now I evaluate for sig figs, and I see that I now need 4 significant figures. So I'm going to do what I always do. I'm going to start on the left-hand side, count the first significant number, and I'm going to go to 4. 1, 2, 3, 4. That one number right there is going to be my helper number. It's super small, so my answer ends up being 3.782. I don't need to round up because that one helper number is low. And my units end up being moles. All right, now there's one more thing to take in account here. Because of Avogadro's law, we now can determine the density of a gas at STP. And once again, it's important to know that it has to be a gas at STP. The mathematical equation for density is still going to be the same. we can still write density equals mass over volume. But because we know Avogadro's law, and because we know that the volume of 1 mole is equal to 22.4, we can actually tweak the mathematical equation a little. We can still have density, but watch what happens. The mass now becomes either the gram formula mass or the gram molecular mass. I'm just going to write one word for now. And the volume ends up being the constant of 22.4 liters. So the formula is essentially the same, but the volume is always going to be 22.4 liters, and I can find the mass just by summing all the elements together. Now, let's take a look at one sample problem for the density of a gas at STP. This problem says that you have the gram formula mass of 30.24 grams, and that they want you to calculate the density of this gas at STP. And once again, it's important to see gas at STP, and it's still going to be density. So I can write the same formula, density equals mass over volume, but I'm going to remember that I can tweak the equation because mass really is just the gram formula mass of 30.24 grams. And my volume, because it's a gas at STP, ends up being 22.4 liters. When you plug this into your magic calculator, you end up getting as your answer density equals 1.35. But I'm not done because I want to evaluate for sig figs. The digit that I'm given in the problem has 4 significant figures. So my answer must also match that number of significant figures. It doesn't, it only has 3 significant figures. So my answer ends up being 1.350. The 0 needs to be there because I need to have 4 significant figures. And the units end up being grams per liter. All right, so you're going to try some independently, and then I'll see you in the next lesson. Bye for now.